In this seminar we'll be talking about PCBs, or printed circuit boards. Printed circuit boards are what we use these days to connect electronic circuits together. It's essentially a fiberglass or FR4 piece of board, and we put copper tracks over it. And there's various methods we'll talk about in a moment of actually putting those copper tracks down. And then we have a bunch of components that will solder onto these printed circuit boards to allow us to connect all the components together and create an electric circuit that actually does something. Now these days, circuit boards can have multiple layers. In the labs we only use 2-layer boards, which means we have copper tracks on one layer and on the other layer. But we can stack these out and have circuit boards with up to 32 layers. You can imagine these are a fair bit more expensive and a fair bit thicker, but allow us to route a whole lot more signals than we would otherwise be able to do with 2 layers.
So let's look at a few of the features on the printed circuit board itself. First thing we notice is there's a whole bunch of what we call tracks, which are the lines on the board. They're lines of copper which connects one component to another component and allows these things to electrically connect to each other. We also have pads, and pads are the small amount of copper around the holes that we actually solder components onto. So we'll notice that all the holes there, we have some shiny metal that we perform the soldering on. So they're the pads. We also have vias, which kind of look like small pads. Now vias are not things that we connect components to, but they're things that allow us to connect from one layer of a board to a different layer on the board. So for our 2-layer board, they allow us to connect from the top layer to the bottom layer, an electrical connection between the layers. We also have footprints, and footprints are the mechanical relationship between the pads. And normally we have a drawing or a footprint overlay to show how the component is meant to sit on the board and how it's actually meant to look. So we have the white overlays on that board to show where all the different components go, which is very helpful for debugging and knowing what a circuit actually does. And we also have planes. Now sometimes our tracks or traces need to be very, very thick. They need to conduct huge amounts of current, or they're connecting to many, many things at once. And so sometimes we'll put down a plane, which is a very large area of track. Generally we'll do it for a ground connection, and can encompass half or maybe even the whole board. We'll now look at a few different ways we can actually make a circuit board, make a PCB. And the 3 most common ways that we make PCBs are silkscreening, photo engraving, and PCB milling. Now at some point we'll need to drill the holes as well in each of these different processes. The first one is the silkscreening method, and we start off with a piece of fiberglass board, FR4 is the general one that's used, and we cover it with a thin layer of copper foil. What we then do is we silkscreen an etch-resistant layer of ink onto this board. So we have a stencil and we put the ink through the stencil and we silkscreen it onto the board. We then put it in some sort of a chemical bath with ferric chloride or ammonium persulfate and etch away all the copper that wasn't coated in this etch-resistant layer of ink. Similarly, the photo engraving technique, we have our copper board and we cover it with a light sensitive ink. The whole board we cover with this. We then place a photo mask, which is essentially an overhead transparency printed with the circuit board layout and how it's meant to look on the copper. We then expose this to UV light for a prescribed amount of time, generally a couple of minutes, and what that will do is the areas that have been exposed to UV light, the areas the light shone through the transparency, those areas will be etched away when we put it in the etching tank, same as with the silkscreening process. The areas that were exposed to UV light won't be etched away, and so they'll form the tracks on the circuit board. Whereas the areas that weren't exposed to UV light, they were blocked by the transparency, will all be etched away. And the final technique is the PCB milling technique. And essentially what we need for this is we need a 3-axis mill with a cutting bit on the end of it, and we put in a blank board, a blank fiberglass copper clad board, and we cut away all the areas of copper that we don't want to use. So a high-speed motor turns the cutting bit very quickly, cuts away the copper. And one of the bonuses of this technique is we can use it to automate our drilling procedure, so we don't need to drill afterwards. This can cut away the copper and perform all our drilling for us. However, the accuracy we get with these PCB milling techniques isn't typically as great, and it's a bit trickier when we're doing multi-layered boards. Now, generally what we'll want to do is cover up all the copper that we're not going to be soldering things specifically to. The reason for this is in the atmosphere, the copper starts to oxidize, and if water and other things get in there, it can actually rust the copper away. So we generally want to cover up all the copper except the area that we're actually going to be soldering to, because obviously we can't cover that up. So we often put onto the board a solder mask, which is a non-conductive layer, generally green, and it leaves everything except the pads exposed. What we can then do on top of the solder mask is put our overlay on. Now this is basically for us to outline where all the components are going to go and give us an idea of where everything is. This is generally white and is very, very helpful for debugging circuits later on down the piece.